Hello and welcome, and in this video we're going to be talking about the graphs of inverse functions. Now, I have two functions here. I have f of x and I have its inverse already found. You should know from the previous video how we find inverse functions. Now I want to jump right into graphing these because there is a nice little relationship amongst inverse functions. So I'm going to go ahead and graph each of these. So you can do this on your own, but I'm going to go ahead and speed this up. So these are our graphs, right? So I have the graph of f of x and I have the graph of its inverse. Now, what I want to take a look at is each of the individual points, and there's actually a nice little relationship amongst these. So for example, I'm just going to pick out a few random points here. So on f of x, I see the point 2, 0. I see the point 0, negative 4. I see the point 6, 8, 6, 8. I see the point, let's say right here, negative 2, negative 8. Now, the interesting thing here with inverse functions and their graphs is that there's a direct relationship between the points of a function and its inverse. What you should see, or what I'll point out to you, is, for example, see on our function f of x, we have the point 2, 0 here. Well, on the inverse, we see the point 0, 2. On our original function, we have the point 6, 8, and on the inverse, we have the point 8, 6. I see the point 0, 4 on the original function, and I see the point negative 4, 0 on its inverse, and I see the point negative 2, negative 8 on this function, and I also see the point negative 8, negative 2 on its inverse. So what you should take away from this is that if we switch the x and the y of the original function, we actually get those points on the inverse function, and that's exactly how we can graph inverse functions. If you're ever given a graph and you're told to graph the inverse, all you necessarily need to do is to flip the x and the y coordinates, because what is happening here is that the graphs of inverse functions are actually the reflection across the line y equals x. If I graph this line y equals x here, I'll do it in dashed line just so we don't confuse and think that this is actually here. But if I graph the line y equals x here, what you should notice is that these two are direct mirror image of one another across that line. So inverse functions graphs are reflected across the line y equals x. And that's actually how the x and the y coordinates end up flipping like that. The other interesting observation here is that since the x and the y's flip, that means the domain and no range flip. So the domain of the original function actually ends up becoming the range of its inverse. And the range of the original function actually ends up becoming the domain of its inverse. So I'm going to go ahead and write that down. So the domain of f of x is the range of the inverse of f of x, and vice versa. So the domain of one becomes the range of the other, and the range of one becomes the domain of another. So what does that all mean? Well, with linear functions, you don't necessarily see it because the domain and range is all real numbers. However, let's say hypothetically speaking, that the domain of some function f of x was, say, 0 to 7, okay, and that the range of that function was, say, negative 2 to positive 8 included on 8, okay. What that means is that the inverse of f of x, would have a domain of negative 2 to positive 8, which was the range of the original, and a range of 0 to 7, which is a domain of the original. So that's what I mean by the domain of f of x becomes a range of the inverse of f of x, and vice versa. And we can see that with another graph. So I'm going to go ahead and plot a function here, and we're going to graph its inverse. All right, so let's say that this is the graph. Let's say that this is the graph of f of x, and we wanted to graph its inverse. Now, the first thing I want to do real quick, just to point out, is I want to talk about what the domain and range of this particular function would be. So the domain of this function, remember, we always read it from left to right. Well, it starts when x is negative 5, and it ends when x is positive 4. And now it does exist at -5, so that would get a bracket. And 4 is open, so that means it's kind of a hole. It doesn't actually exist there, so that would get a parenthesis, right? That's a bad parenthesis. Let me redo that parenthesis. Parenthesis. Now the range, remember, is all the y values, so read it from bottom to top, okay? So it starts when y is 2, and it ends when y is 5. And 2 is included. 2 is included and 5 is open, so it's a parenthesis, okay? Now let's say we wanted to graph its inverse. Well, right away, I'm going to go ahead and graph the inverse in this color here. I can actually state what the domain and range would be without even looking at the graph or even graphing it at all, because there is a direct relationship between inverse functions and its domain and range. The range of the original function would end up actually becoming the domain of the inverse, and the domain of the original is actually going to end up becoming the range of the inverse. And I know this for a fact, and we can go ahead and graph this just to verify. So remember, the way that the relationship here is that we switch the x and the y coordinates. That's why the domain and range end up getting flipped. So the point -5, +2, the point -5, +2 becomes a point 2, -5. Okay. And the point -2, +3, the point -2, +3 becomes a point 3, -2. And the point 1, +4 becomes a point 4, 1. And a point 4, 5, open, becomes a point 5, 4, open. And this would end up being our graph. This would end up being the inverse. I switch all the x and the y coordinates. And as we can see, the domain starts when x is 2 and it ends when x is 5. That's exactly what I said it would have been. And it starts for the range, it starts when y is -5 and it ends when y is +4, which is exactly what we see here. So this would end up being the inverse of f of x. And if I were to go ahead and graph the line y equals x, we would once again see it being perfectly reflected across that line. So as we can see, it is a perfect mirror image across the line y equals x. That's because that is the relationship within functions. The graphs themselves are a direct reflection over the line y equals x. That's what enables the y and the x to switch, and that's what enables a domain and range to switch. So that is a relationship between inverse functions graphs. Between inverse functions graphs, okay? So I hope this video was helpful. If you have any questions, please make sure you let me know, and make sure that you keep this in the back of your head, because we will be covering inverse functions with quadratics, with square roots, cubics, cube roots, exponentials, logs, all sorts of stuff. So make sure you keep all this inverse stuff in the back of your mind. Like I said, I hope this video was helpful. If there's any questions, make sure you let me know, and I'll look forward to seeing you guys in the next video.